Good morning, everyone. Today we are going to talk about the Infineon project that we are honored to be on, the Programmable Load Slammer. Here are the distinguished technical directors from Infineon: Yang Zhu, Applications and Product Definition Engineer, and Kumar Gandharva, Applications and Systems Engineer. And we are Team Infineon: Noah Gibb, Computer Engineer and Electrical Engineer, and myself, Abraham DiMartino, Electrical Engineer. Infineon is a world leader in semiconductor solutions, and it was founded in 1999 in Germany when it was spun off from Siemens. It currently has about 47,000 employees worldwide and had a revenue for fiscal year 2019 of approximately $10 billion. It runs 54 R&D locations and has 21 manufacturing locations. We worked with the Rhode Island location, which creates and develops power management products. I am going to start with some background information for the motivation into why load slammers are a necessity in today's voltage-regulated world. These days, most voltage regulators are built onto the same board as a CPU or GPU, but before this can happen, a robust test must be performed to make sure the voltage regulator will be able to meet or exceed the specifications for that GPU or CPU. For this example of the GPU on this slide, going from sleep mode to full gaming mode, the voltage needs to stay constant, but the current being drawn makes it hard to do so. In this GPU example, if it needs a constant 1 volt, and when the GPU ramps up to full gaming mode, its power requirement is 78 watts, this equates to about 78 amps of current draw. This is a current ramp with a very fast slew rate. Typical commercial electronic loads cannot emulate this, and the current draw in some chips can go up to 1,000 amps per microsecond of low transients. Of course, the voltage regulator needs to be tested to see how it handles that very quick change in current, and that is where the load slammer comes in. As we can see in this picture on the left, voltage regulator modules can have some serious heat sinks to deal with all of the fluctuations in current. This picture on the right, I just wanted to show the capacitor, MOSFET, and inductor banks on the voltage regulator module for absorbing and smoothing of the large amounts of current. With the precision and accuracy of a load slammer test, sometimes you can make these banks smaller than what was initially calculated. The dynamics at play need to be under control and within certain set parameters to be able to stay away from a game ending early because of an overheated voltage regulator that had to shut down. The testing of voltage regulators has needed to evolve, and so companies such as Infineon have built these load slammers in-house that test for the transients that occur due to large swings in current. These systems work but are not reliable and robust at being repeatable with the exact same conditions each test. To address this, Infineon has brought this team together to achieve a better mousetrap. This is the setup that is being used right now at Infineon to test voltage regulator modules. As you can see, it is not a product but a rat's nest of different components. This setup has a low probability of being repeated with the same parameters and confidence. The components are the function generator, a synchronous controller, load slammers, a current sensor, and on the board is the device under test. For this project, we are being very ambitious, and we want to put all of these components into one device called the load slammer. To achieve our ABO, we need to design, build, and test a single PCB device that is microcontroller based. This PCB needs to be able to slam at least 50 amps at the device under test. It needs to have a built-in arbitrary function generator that can produce arbitrary waveforms of up to 10 kHz. We need a special trapezoidal signal built in that can reach 100 MHz with a buffer of 1 to 2 MHz on the top end. This trapezoidal signal needs to have an adjustable slew rate, duty cycle, and amplitude. And all of the functions need to be controlled by an easy-to-use GUI with data capture in real time. So I am happy to announce we are mostly on track to achieving the ABO. At this point, we have the final schematic with the PSoC microcontroller on it and the load slammer circuit on it. We were having a little trouble getting actual components that can be ordered onto the final schematic, and so we might have to start that in the beginning of January and have the PCB manufactured at the end of January, with a return to test time of hopefully middle of February. We have built and tested a working trapezoidal generator at 1 MHz with adjustable slew rate, duty cycle, and amplitude using the PSoC 5LP development board. We have communicated with the board using Python and have a GUI that has a 3D graphing ability using tk-plot from MATLAB. The GUI was done using Python tkinter, and at this point, we really need to thank Nick Lovett for putting in the work over the summer and giving us a great head start on the GUI design. This project will reduce the number of function generators required with today's load boards, a savings of approximately $10,000 for the next few years. This project will also save valuable engineer, technician, and customer validation time by simplifying setup and storing preloaded transient profiles on our demonstration boards. The 3D transient feature will help find weaknesses in designs, further saving validation time and customer relationship impacts due to marginal systems. The field and application engineers will receive these tools to enable customer validation. This tool can enable Infineon's customers with their own electronic loads, which can lead to customers buying Infineon products. Validation time savings, preventing marginal customer problems, and cell enablement could exceed $50,000 annually, which is a big economic impact. So here we have a diagram of how the load slammer circuit works and the waveforms that we need to replicate and test. The voltage regulator is in the top left and the load slammer is the lower picture. In this top right diagram, there is a picture showing the max overshoot and the minimum undershoot voltage, which would be checked with the specifications of the chip to see if it passes. The middle current waveform is the slamming current, and the last waveform is the AC voltage and the feedback voltage following the spike in the replication of the electronic load. I am now going to talk about my technical contributions to this exciting project. First, I will discuss the OrCAD PSpice design and simulation, and then the partially finished schematic. Then I will discuss the PSoC 5LP and Pixock Creator, and then finally I will discuss the development of a trapezoidal waveform generator. The first component we are putting into our device is the load slammer, and for the hardware design specifications, we needed this circuit similar to as shown. Over on the upper right is the device under test connected to the drain of the Infineon NMOS. We had to test the full range of possible voltages that might be used. This was designed to be between 0.5 to 5.5 volts. On the NMOS source is where we have the pulsed 50 amps. To do this, we used a Texas Instruments operational amplifier and an Infineon NMOS high current component. We had a feedback loop of capacitors and resistors on the op-amp and a ratio of sense resistors on the source leg of the NMOS to maintain the amperage we wanted. This was simulated and tested to achieve the desired results for all the different load voltages. The circuit has been designed and works to spec at this time. There does not exist over on the left a component called the pulse generator in the real world. So the component that is going to be put there is the PSoC microcontroller. Getting all of the actual components that Infineon would use to generate the BOM, bill of materials, did not happen. So the final schematic is not at the point where it can be handed over to PCB design, unfortunately. Hopefully at the beginning of next semester, that will be the first action item to be completed. So in order to design a trapezoidal waveform generator, we had to first learn a new development tool that is the PSoC 5LP development board and Pixock Creator, the IDE integrated development environment that goes with it. The PSoC 5LP is a true programmable embedded system on a chip, integrating custom analog and digital peripheral functions, memory, and an ARM Cortex M3 microcontroller on a single chip. This type of system is different from most mixed-signal embedded systems, which use a combination of a microcontroller unit and external analog and digital peripherals, such as op-amps, ADCs, and application-specific integrated circuits, ASICs. A single PSoC device can integrate as many as 100 digital and analog peripheral functions, reducing design time, board space, power consumption, and system costs while improving system quality. Programmable digital and analog peripherals enable custom functions and flexible routing of any analog or digital peripheral function to any pin. In this slide, we are showing Pixock Creator, which is a free Windows-based IDE that enables concurrent hardware and firmware design of systems. On the far right here is where the built-in components are, and also the external off-board components are picked. In the middle is the main design workspace, where everything is designed using drag and drop components to build your hardware system. Each component has built-in parameters and a data sheet to explain how it works. Once the design is complete, you can build it virtually, and the firmware is created and all the files that go with it over on the left here. Finally, you can plug in your board and program it to test what you have built. This is an intuitive platform, but there is a lot going on behind the scenes, and we definitely spent a lot of time learning how the program works and the limits of what it can do for our project. It is priced very low for what it offers, but with a small price comes limitations that we ran into and will be talked about in the next slide. Here is just one example of the variations that were built and tested to accomplish the task of meeting the spec of 1 MHz trapezoidal waveform generator with adjustable slew rate, duty cycle, and amplitude. One of the limitations we ran into was the normal clock speeds not being fast enough to run the digital to analog converters that were supposed to produce the waveforms we needed. This was fixed by overclocking, and as with any system that is pushed to its limits, it gave us some stability issues. Trying to get stable working trapezoidal waveform generator led us down many paths, including becoming part of the Cypress community online to research what had been done to address the top-end limitations of this board. Some people had designed their own components using digital memory access, DMA, and others said that we would have to move to an FPGA, field programmable gate array, to achieve what we wanted. In the end, we were able to come up with a working solution. That puts the trapezoidal function generator on the load slammer board. So at this point, we have integrated the load slammer and the trapezoidal generator. We still need to put the arbitrary waveform generator in and need an easy-to-use GUI communicating and controlling the load slammer to complete the one package design. My partner Noah is going to present those last topics to you in the next few slides. Thank you.
Hi, I'm Noah Gibb, and I'm going to be talking about my individual technical contributions to this project, beginning with the hardware development and moving to software. In hardware, a significant portion of time was spent trying to create an arbitrary waveform generator. Per our specifications, the arbitrary waveform generator only needed to be implemented for a maximum of 10 kHz. The PSoC 5 features the WaveDAC 8 component, which can generate completely arbitrary waveforms using the internal voltage and current sources, but operates at a low internal frequency. By connecting an external clock to the WaveDAC 8, the frequency can be increased to meet our specifications while any arbitrary waveform can be produced. In software, communication between PSoC and Python was established over the USB bus. This allows the board to run at an increased maximum frequency of 48 MHz. In Cypress Creator, the PSoC device is set to loop continuously and open its ports to the USB data bus. The board then waits for a command to be issued over that data bus, which will most likely be coming from Python here, before its pins and memory is accessed and performs a command. This will enable the PSoC to be controlled from the Python-based GUI and allow for parameters to be changed immediately rather than reprogramming the entire board. This approach for Python to PSoC communication requires that the two USB ports on the PSoC are used. When the PSoC is initially programmed, it will need to be connected by its J2 programming USB port, and when communication is established, it will need to be connected over the J1 communications port. This eliminates the need for the miniprog4, a USB serial debugger and programmer that was originally used for this communication. Instead, the PSoC can be directly accessed over the USB bus once the proper drivers are set up. Elimination of the miniprog decreases project cost as well as simplifies the end design, as it will use less components. Our future technical accomplishments for next semester begin with testing and validating the PCB of our hardware design. Once the PCB is fabricated, we will be able to verify the electrical specifications for current, frequency, and slew rate. With the PCB load slammer, we will then be testing the functionality of the GUI for its real-time data collection capabilities and modifying it as needed. The GUI will be edited to interface with the PSoC and functions added to install and update drivers. Once this is complete, our focus will shift to storing and retrieving data from the PSoC board using the GUI and the management of that data. We have a high degree of confidence that by the end of next semester, we will be able to complete all of these tasks. Team Infineon would like to thank our great technical directors, Yong Zhu, Danny Clavet, Kumar Gandharva, and our excellent professor, Dr. Sunak, for their support and guidance during this project. Thank you.